Tonight, beyond the small gravitational neighborhood we call home, the distances between galaxies are growing while you listen. Most people believe the hard part of space is the distance between stars. It is not. The truly unthinkable distances begin where the stars end, in the dark between galaxies. A dark so wide that light itself, the fastest thing that exists, spends millions of years crossing it and arrives stretched, red-haired, and faint. Tonight, we are going to walk that dark honestly, one quiet layer at a time, and find out why the distance between galaxies is not just larger than you think, out beyond everything bound to us. It is getting larger while you sleep. That sounds like it should be frightening. By the end of tonight, I think you will find it is one of the most peaceful facts in the universe. So dim the lights. Let the day set itself down. There is nothing to memorize, and nowhere to hurry. Let us begin. Picture the most famous photograph of space you can remember. Maybe it is a spiral galaxy, glowing softly against the black, its arms curled like cream, stirred slowly into coffee. Maybe it is one of those deep field images, hundreds of tiny galaxies scattered across a single frame like sand tossed onto dark velvet. Maybe it is just a poster from a classroom wall, the kind with a few painted galaxies floating in the background, close enough together that they almost seem to be keeping each other company. Every one of those images is beautiful, and every one of them, in one very specific and very forgivable way, is lying to you. Not about what exists. The galaxies are real. The colors are usually built from real data, gathered by real instruments, checked by careful people. What the images cannot show you, what no image has ever been able to show you, is the distance, the space between things. Because if a photograph tried to show the true emptiness between two galaxies at an honest scale, the galaxies themselves would shrink to invisible specks, and you would be left staring at a completely black rectangle. Nobody prints that poster. So instead, every image you have ever seen quietly compresses the universe, folding millions of years of light travel into a few inches of paper, just so there would be something left for your eyes to enjoy. For a while, nothing here needs anything from you. The pictures can simply sit in memory, exactly as they are. There is a strange side effect to growing up, surrounded by those compressed pictures. Somewhere deep in your intuition, without ever deciding to, you learned a scale for the universe that is wrong by a factor so large there is no everyday word for it. You learned that galaxies drift near each other like boats on the same calm lake. You learned that the black between them is a thin gap, a pause, a comma. That intuition is not your fault. It was assembled, image by image, from decades of pictures that all had to make the same practical choice: shrink the distance, or show nothing at all. Tonight, we are going to make the opposite choice. Tonight, the distance itself is the destination. And I want to be honest with you right at the start about what that means. Because this journey has a shape, and knowing the shape may help you settle into it. We are going to move outward slowly. We will start inside our own galaxy, a place that already strains the imagination, and we will only leave it once you can genuinely feel its size rather than just hear the number. Then we will cross to the nearest great galaxy beyond our own, then to the neighborhood of galaxies we live in, and to the question of whether neighbors that large ever meet. Then, out to where neighborhoods give way to something vaster, to the largest pattern anyone has ever mapped. And finally, to the discovery that the distances out there are not even sitting still. They are growing, quietly, right now, in the dark above your roof. And at the very end, we will come all the way back down to this room and find out why none of it was ever aimed at you. If you drift off somewhere in the middle, that is fine. Everything out there has been patient for billions of years. It can certainly be patient with you. Here is a small, true story about how badly our intuition wants to shrink these distances, and how long that instinct has been with us. When astronomers in past centuries looked through their telescopes at certain faint smudges of light in the night sky, smudges we now know were entire galaxies containing hundreds of billions of stars. Many of them reasonably concluded that these were small clouds of glowing gas, sitting quietly inside our own Milky Way, perhaps a few thousand light years away at most. The idea that each smudge might be another Milky Way entirely, separated from us by a gulf 1,000 times wider than our whole galaxy, was on the table, and some thinkers argued for it. But to many careful scientists, it simply felt too big to be true. The universe, surely, could not be that empty or that large. We will meet the people who settled that argument a little later tonight. On a specific night in the 1920s, with a single photograph and a single misbehaving star. For now, just notice the instinct itself. Even trained astronomers, staring at real data, wanted the universe to be smaller than it was. Your intuition is in very good company, and tonight it gets to be corrected gently, the way theirs was. One honest measurement at a time. The room around you can grow a little dimmer in your attention now, and the sky above it a little wider. I want to give you one honest image before this chapter closes. A single picture to carry into everything that follows. On a clear autumn night in the northern hemisphere, away from city lights, you can see the Andromeda galaxy with your bare eyes. It looks like a faint, elongated smudge, small enough to cover with your fingertip held at arm's length. Here is the part almost nobody realizes. That smudge is only the bright central core of Andromeda, the full galaxy. If your eyes were sensitive enough to gather all of its light, would stretch across a patch of sky several times wider than the full moon. There is an enormous spiral galaxy hanging in your sky right now, wider than the moon, and you have probably never noticed it, because its light arrives spread so thin, after a journey of 2.5 million years, that your eyes simply cannot collect enough of it to see the whole shape. The problem was never that the universe is hiding. The universe is enormous and luminous and practically shouting. The problem is that the distances thin the light. Every particle of light that reaches your eye from Andromeda left home before our species existed, crossed a darkness with almost nothing in it, and arrived at your window as barely a whisper of itself. The distance did that. The distance does that to everything. And that same distance is what every poster, every textbook, every gorgeous space documentary has spent your whole life politely editing out. Tonight we put it back in, because before we can honestly feel the distance between galaxies, we need something no classroom poster ever gave us. We need a ruler, not a ruler made of miles or kilometers. Those break down almost immediately out here. but a ruler made of the only thing fast enough and steady enough to measure the dark itself. A ruler made of light, and building that ruler, slowly, piece by piece, is exactly where our journey goes next. Every journey needs a way to measure itself, and ours begins with a simple confession. The units you use every day, the miles between cities, the minutes between appointments, were invented by creatures who rarely traveled farther than the horizon. They work beautifully for a road trip. They collapse almost instantly in space. Neptune, the most distant planet from the Sun, sits nearly 3 billion miles away. And if you are honest with yourself, that number already means almost nothing. Say 3 billion slowly, and your mind does not picture a distance. It pictures static. A wall of zeros with nothing standing behind it. And Neptune, on the scale of tonight's journey, is not even the front porch. So, astronomers long ago stopped measuring the universe in miles and started measuring it in light. The idea rests on one of the older discoveries in modern science. And the discovery itself is worth a slow minute, because it began with a mystery about a moon. In the 1670s, a Danish astronomer named Ole Rømer was studying the moons of Jupiter, timing the moments when the innermost moon slipped into Jupiter's shadow. Those eclipses should have ticked along like clockwork. Instead, Rømer noticed they ran early when Earth was closer to Jupiter and late when Earth was farther away, by a difference that eventually added up to many minutes. His explanation was quietly revolutionary. Light was not instantaneous. It took time to cross space. And when Earth was farther from Jupiter, the news of each eclipse simply took longer to arrive. Light, the thing everyone had assumed simply was, turned out to travel, and its speed could be estimated by watching a moon keep imperfect time. We now know that speed with great precision, in a single second, light travels about 186,000 miles, fast enough to circle the entire Earth roughly 7 times before you finish saying the word 7. And that speed is a constant, the same everywhere, the same in every direction, which makes it the one truly universal ruler reality ever handed us. Instead of asking how many miles away something is, astronomers ask a calmer question. How long does light take to get there? Let us practice with it, unhurried, because the practice itself has a rhythm that suits this hour. Light crosses the distance from the Earth to the Moon in about 1¼ seconds. When Mission Control spoke with astronauts standing on the Moon in 1969, every exchange carried that delay. A pause of more than 2 seconds for the round trip, a silence you can genuinely hear in the old recordings if you listen for it. A small gap where 250,000 miles sat inside the conversation. Light from the sun takes about 8 minutes to reach your face. Every sunrise you have ever watched was already 8 minutes old before its first color reached you. Light reaches Neptune in a little over 4 hours. So, the entire solar system, the sun, and all 8 planets, everything most of us were taught to think of as vast, fits inside a single afternoon of light travel. An afternoon, hold the smallness of that, because we are about to spend far more. Now the step that changes everything. Let light run, uninterrupted, at the fastest speed the universe allows, for 1 full year. And the distance it covers is what astronomers call a light year. Written out in miles. 1 light year is close to 6 trillion miles. But the miles are not the point. And the number can pass without being kept. The point is the time. A light year is a distance so wide that the fastest thing in existence needs an entire year of your life to cross it. And here the universe begins to show its true proportions. The nearest star to our Sun, a small red star called Proxima Centauri, sits about 4¼ light years away. Not 4 light hours, 4¼ light years. The gap between our Sun and its very closest neighbor is roughly 9,000 times wider than the entire solar system we just crossed in an afternoon. Because numbers alone slide off the mind at this hour, let us build a small model together, one you can keep nearby for the rest of the journey. Shrink the Sun down to the size of a grapefruit and set it in the middle of an empty parking lot somewhere in Kansas. In the middle of America. On that scale, the Earth is a grain of sand about 35 feet away. Neptune, the outer edge of the planetary family, is a slightly larger grain, about 1/5 of a mile out. A pleasant evening walk from the grapefruit. Now, on that same scale, where is Proxima Centauri, the nearest star? It is another grapefruit, resting roughly 1,800 miles away, somewhere near the far western edge of the continent. 2 pieces of fruit, most of a country apart, with essentially nothing in between but air and distance. That is what the word nearest means between stars. Everything else in the night sky is farther, most of it enormously farther. There is a strange comfort hiding inside that model, and it is worth naming before we move on. All that emptiness is why the sky is so still. Nothing jostles, nothing crowds. The stars keep to their own vast rooms, and the quiet you feel when you look up at night is not an illusion. It is the actual condition of things, measured and confirmed. This is the ruler most space stories stop at. The light year, the near continent between grapefruits. It already feels like the ceiling of imagination. But tonight's journey is about the distance between galaxies, and for that, even the light year turns out to be a unit for short errands. Astronomers who map the universe beyond our galaxy rarely count in single light years. The way you would not measure the distance between New York and Los Angeles in inches, they count in millions of light years. And on the very largest charts, they use a professional's unit called the megaparsec, a single tick mark equal to about 3¼ million light years. The word itself can drift away the moment you hear it. What matters is what it implies. Somewhere tonight, there are working scientists for whom 3 million years of light travel is one small step on a map, the way an inch is on yours. So here is where our ruler stands as this chapter closes. Laid out plainly, with nothing hidden. Light crosses your bedroom in about 1/1000th of a second. It crosses the solar system in an afternoon. It crosses to the nearest star in a little over 4 years. And the journey we are preparing to take, out into the space between galaxies, will be measured in millions of years of light travel, a duration longer than our species has existed, for a single one-way trip of a single beam of light. But before we spend those millions, we have one piece of unfinished business, and it is a piece most space documentaries hurry past. We have never actually felt the size of our own galaxy, the one we live inside, the one every beam of light must first escape before the true dark even begins. Crossing your own home, it turns out, is already a journey worth an entire chapter. That is where we go next. And the front door is closer than you think. You live inside a structure so large that no one has ever seen it from the outside. And no one alive tonight ever will. That is not a poetic exaggeration. It is a plain statement about the Milky Way, the galaxy that holds our sun. Every star you have ever seen with your bare eyes. And, by most current estimates, somewhere between 100 billion and 400 billion stars in total. The honest range is that wide because counting stars in a galaxy you are trapped inside is genuinely difficult. Like trying to count the trees in a forest while standing in the middle of it, in fog. At night, astronomers count carefully in the regions they can see clearly, then estimate the rest from the galaxy's mass and light. And different, careful methods land on different totals. So when you hear a single, confident number for the stars in the Milky Way, it is worth knowing the real answer is a range. And the range itself is wider than most nations' populations, multiplied by anything you like. Here is the shape of home, as best we can chart it from the inside. The Milky Way is a spiral of stars, gas, and dust, a flattened disk with a bright central bulge. And from edge to edge, that disk spans roughly 100,000 light-years. Feel that against the ruler we just built. 4 light-years brought us the near continent between 2 grapefruits, the gap to a single neighboring star. The galaxy is 25,000 of those gaps laid end to end, and not in one direction only, but woven through a slowly turning wheel of hundreds of billions of stars. To make the time feel real, pick a moment from deep human history. Roughly 100,000 years ago, bands of modern humans were beginning the long migrations that would eventually carry our species across the entire world. A beam of light entering one edge of the Milky Way in that era, when those first travelers were setting out, would only now, tonight, be arriving at the far side. One crossing of our home, at the fastest speed there is, costs the whole story of human wandering. The galaxy does not need your attention to keep turning, and it will not hurry for anyone. That is rather the point of it. Our sun sits a little more than halfway out from the center, in a comparatively quiet region between 2 of the major spiral features, which may be part of why our corner of the sky is as calm as it is, though how much that has actually mattered to life on Earth remains an open question. And the whole neighborhood is moving. The sun, carrying the Earth and everyone you love, is traveling around the center of the galaxy at roughly 500,000 miles per hour. That sounds violent. It is the smoothest ride you will ever take. So smooth that no one aboard has ever felt it. At that enormous speed, one full lap around the Milky Way still takes about 230 million years. The last time our solar system passed through this part of its orbit, the dinosaurs were just beginning. Every single thing recorded in human history, every city, every language, every name ever spoken, fits inside a sliver of one galactic lap, so thin it barely counts as motion at all. Now let us measure humanity against the house we live in. Honestly, because the honesty here is strangely calming. The farthest any human beings have ever traveled is the moon, about 1.25 light seconds away. The farthest any machine has traveled is the Voyager 1 spacecraft, launched in 1977, now the most distant human-made object in existence. After nearly 50 years of continuous flight, Voyager 1 is a little less than 1 light day from Earth. Not 1 light year, 1 light day. If the Milky Way were a map spread across the entire United States, the total reach of every spacecraft our species has ever launched would fit comfortably inside a single footprint. There is one more human signal worth measuring, and it is the most far-reaching thing we have ever made. Radio. Our earliest strong broadcasts have been spreading outward from Earth for roughly a century, which means there is a growing sphere of human transmissions, expanding at the speed of light. Currently, a bit over 100 light-years in radius. It is sometimes described as a sphere of voices and music, and in spirit it is. Though honesty asks for one added line. Most of those signals thin out so quickly with distance that near the edge of that sphere they would be far too faint for anyone to recognize as voices or music at all. A whisper dissolved almost entirely back into the static of the sky. Even so, take the sphere at its full, generous size. A century of our loudest broadcasting, moving at the fastest speed possible, has covered about 0.1% of the width of our own galaxy. If the Milky Way were a concert hall, we have hummed quietly into our own sleeve. None of this is said to make humanity feel small in a painful way. Quite the opposite. It means that everything we have ever known has happened inside a single quiet corner of a single spiral arm. And that corner has been enough to hold all of it. Every symphony, every grandmother's kitchen, every night sky that ever made someone fall in love with the stars. The house is unimaginably large. The room we live in is warm. And the walls have held, before we leave that room, one last picture, the one this whole chapter was built to give you. On a dark summer night, far from city lights, you can see a soft band of pale light arching across the entire sky. People have called it the Milky Way for thousands of years, and many assumed it was cloud, or mist, or something painted on the dome of heaven. In 1610, when Galileo Galilei pointed one of the first telescopes at that band, it resolved into countless individual stars, too many and too faint for the bare eye to separate. That band is our galaxy's disk, seen edge on, from the inside. When you look at it, you are not looking up at the Milky Way. You are looking along it, down the length of your own home, through tens of thousands of light years of stars whose light has merged into a single glowing fog. And here is the thought to rest on as the chapter closes. Every one of those thousands upon thousands of stars, and the hundreds of billions more hidden behind and beyond them, all of it together, the entire 100,000 light-year wheel, is one object, one single galaxy, one item in tonight's inventory. The universe we are about to step into holds, by estimates drawn from deep survey images, hundreds of billions of galaxies at minimum, and quite possibly a great many more. Everything you have ever seen in the night sky with your bare eyes, with one single faint exception, belongs to this one galaxy. Next, we go to meet the exception. It is a smudge of light in the autumn sky. It is 2.5 million light years away. And the story of the night humanity finally understood what it was is one of the finest stories science has ever told. A story with a public argument. A quiet woman at a desk in Massachusetts. a mislabeled star, and a man on a mountaintop who crossed out a single letter and changed the size of everything. Let me take you back a little over a century, to a time when the smartest people on Earth genuinely did not know whether the universe contained one galaxy or billions. It is worth pausing on how recent that is. Your great-grandparents may already have been alive. There were automobiles on the roads and jazz on the radio. And yet the question of whether the Milky Way was the entire universe or just one island among countless others remained completely unsettled. Astronomers could see the mysterious spiral smudges in their telescopes. They had been cataloguing them for over a century. What nobody could do was measure how far away they were. And without a distance, both answers stayed alive. Either the spirals were small clouds of gas drifting inside our own galaxy, or they were entire other Milky Ways, so remote that their hundreds of billions of stars blurred into a single faint stain of light. In April of 1920, the disagreement became famous. Two respected astronomers, Harlow Shapley and Heber Curtis, met at the Smithsonian in Washington to argue the matter publicly. In an event historians of science still call the Great Debate. The evening actually ranged across several connected questions: the true size of the Milky Way, the sun's position inside it, and what the spiral smudges were. But the fate of the spirals became its most famous legacy. Shapley argued they were nearby, part of one enormous Milky Way that was itself essentially the whole universe. Curtis argued they were distant island universes in their own right. Both men were careful. Both used the best evidence available. And the honest outcome of that famous evening is that neither side could prove its case, because the single missing ingredient, a reliable way to measure such enormous distances, had not yet been applied to the spirals. The strange thing is that the ingredient already existed. It had been forged years earlier, in a quiet office in Massachusetts, by a person the evening's audience mostly did not know to thank. Her name was Henrietta Swan Leavitt, and she worked at the Harvard College Observatory as what was then called a computer, one of a group of women hired to measure and catalogue the brightness of stars on photographic plates. Patient, meticulous work that the male astronomers of the era largely handed off. Leavitt was assigned to study variable stars, stars whose brightness rises and falls in a steady rhythm, and she focused on a particular family of them called Cepheids, examining thousands of these stars. She noticed something in 1908 and confirmed it by 1912. A pattern hiding in plain sight. The brighter a Cepheid truly was, the more slowly it pulsed. The rhythm and the brightness were locked together, dependably, like the length of a pendulum and the pace of its swing. Feel what that quietly makes possible. If you can watch a Cepheid pulse, you can time its rhythm. From the rhythm, Leavitt's relationship tells you how bright the star truly is. Compare that true brightness with how faint the star appears from Earth, and the dimming tells you the distance. The same way you can judge how far away a car is at night if you know how bright its headlights really are. A star's heartbeat had become a ruler. It remains one of the most elegant measuring tools ever discovered. And Leavitt found it not at a telescope on a mountaintop, but at a disk. In the numbers. Plate after plate after plate. She was never awarded a Nobel Prize for it. A member of the Swedish Academy began paperwork toward nominating her in 1925. only to learn she had died of cancer 4 years earlier, at 53, before the full consequences of her ruler had reached the world. Those consequences arrived through another person, on a mountain in California. And that is the night this chapter is named for. His name was Edwin Hubble, and tall, pipe-smoking Missourian, working at the Mount Wilson Observatory above Los Angeles, home of the Hooker telescope, then the most powerful telescope on Earth, with a mirror 100 inches across. In the autumn of 1923, Hubble was photographing the great spiral in Andromeda, the same faint autumn smudge we have been circling all night, hunting for exploding stars called novae. On the night of October 5th, into the early hours of October 6th, he exposed a glass photographic plate of one of the spiral's arms and found 3 candidate novae. He marked each one with the letter N. Then, comparing his plate against earlier photographs of the same region, he noticed that one of those 3 points of light was misbehaving. A nova flares once and fades. This star had brightened and faded and brightened again, in a repeating rhythm. It was not a nova at all. It was a Cepheid, a pulsing star of exactly the kind Leavitt had turned into a ruler. On the plate, Hubble crossed out the N beside it and wrote, in slanted letters, the abbreviation VAR, short for variable, followed by an exclamation point. That small handwritten correction on a piece of glass is one of the most consequential edits in the history of science. And the plate itself, with the crossed-out letter still visible, is preserved to this day. Because now the calculation was almost simple. Hubble timed the star's rhythm, applied Leavitt's relationship, compared true brightness to apparent faintness, and out came a distance. The number he calculated was close to 1,000,000 light-years, a figure later revised upward as the ruler itself was refined. But even that first estimate settled everything on the spot. 1,000,000 light-years placed the star, and the entire spiral it lived inside, far beyond any defensible edge of the Milky Way. The smudge in Andromeda was not a cloud in our galaxy. It was another galaxy, an island of its own, at a distance no human mind had ever been asked to hold before. When word of the finding reached Harlow Shapley, the man who had publicly argued the Milky Way was the whole universe, he is reported to have told a colleague that this was the letter that destroyed his universe. What actually happened, of course, is quieter and kinder than destruction. Nothing in the sky changed that autumn. Andromeda did not move 1 inch. Only the map changed. The universe had been that large all along, patiently, for billions of years, waiting for a species on one small planet to finish building a ruler accurate enough to notice. Within a couple of years, Hubble had confirmed Cepheids in other spirals as well. And by the end of the 1920s, the old argument was fully over. The universe was made of galaxies, plural, uncounted, scattered through a darkness far deeper than anyone at that Washington debate had dared to defend. 3 people, none of whom set out to redraw reality, had done exactly that between them. A woman at a desk who found the ruler, a man at a debate who guessed right without proof, and a man on a mountain who crossed out one letter and measured the answer. The very first of those confirmed galaxies, the one whose single pulsing star opened the door, is still hanging in your autumn sky tonight, covering a patch wider than the full moon. Its light, arriving from a distance, we finally, honestly measured. So now, Let us go there properly, across the whole gulf at last, and feel what 2.5 million light-years actually means when it is yours to cross. The Andromeda Galaxy is the nearest large galaxy to our own, and everything difficult about tonight's subject is contained in that one sentence. Because the word nearest and the measurement 2.5 million light-years both belong to the same object. Let us feel the gulf the honest way, with time first, because time is the ruler we built together, the light entering your eye from Andromeda tonight. If you find it in a dark autumn sky, left that galaxy roughly 2.5 million years ago, when those particles of light began their journey, there were no modern humans anywhere on Earth. Our distant ancestors of that era were early members of the human family, already making some of the earliest widely known stone tools. Every step of what followed — fire, language, ice age, farming, the first cities, the pyramids, every empire, every song ever sung — all of it happened while that light was in flight, crossing a darkness with almost nothing in it. It arrives tonight, lands on the back of your eye, and the journey ends in you. You are the destination of a beam of light older than your species. It has been traveling your whole life, and everyone's whole life, and it was never once in a hurry. Now let us feel the same gulf with our small model, because the model is about to earn its keep. If we shrink the entire Milky Way, all 100,000 light-years of it, down to the size of a dinner plate resting on your kitchen table, then Andromeda, on that same scale, is a slightly larger plate sitting about 20 feet away. Across the room, or just into the next one, 2 dinner plates, 1 house. That is the true scale of the gap between neighboring large galaxies. And here I owe you a moment of honest surprise. Because if you have been listening closely all night, that number should feel wrong. Remember the stars. When we shrank the sun to a grapefruit, the nearest star was another grapefruit most of a country away. 1,800 miles of emptiness between 2 pieces of fruit. Stars are separated by tens of millions of times their own size. But galaxies, measured against their own enormous width, are close together. Andromeda sits only a few dozen Milky Way diameters away. Proportionally speaking, galaxies are dinner plates in the same house, while stars are grapefruits on separate coasts. The universe is far emptier between stars, relative to their size, than it is between galaxies. Almost nobody's intuition expects that, and it is one of the quiet keys to this whole journey. Hold it loosely. In 2 chapters, it is going to matter enormously. The neighbor itself rewards a closer look. Andromeda is a spiral, like our home, but grander in span. Measurements suggest its glowing disk stretches considerably wider than the Milky Way's, perhaps around twice as wide by some accountings, and it carries, by many estimates, somewhere near 1 trillion stars. Compared with our few 100 billion, the honest caveat, in keeping with tonight's promise, is that weighing and measuring a galaxy is delicate work even from outside it. And published figures for both galaxies have shifted over the years as instruments improved. What no one disputes is the pairing. Andromeda and the Milky Way are the 2 great spirals of our corner of the universe, comparable in scale, gravitationally aware of each other, each one appearing in the other's sky. If there are eyes on some world in Andromeda tonight, looking back this way, they see a faint, elongated smudge in their own darkness. Our entire galaxy, every star you have ever seen, all of human history, compressed into a stain of light small enough to cover with a fingertip. There is a strange wrinkle in all of this that deserves a slow moment. When you look at Andromeda, you are seeing a 2.5 million year old portrait, not a live image. Every observation in astronomy carries some delay. But out here, the delay becomes impossible to ignore. Andromeda as it is right now, tonight, in this very moment, is something no one on Earth can see, and no one will be able to see for another 2.5 million years. Across a gap this wide, the phrase right now begins to lose its grip. And later tonight, when we discover what the gaps themselves are doing, that strange fact will return with much deeper consequences. Before the chapter closes, its most surprising gift, and it is a double one. First, remember that Andromeda in your sky is wider than the full moon, several times wider, and you have never noticed, because 2.5 million light-years of travel spreads its light thinner than your eyes can gather. You have lived your entire life beneath an enormous spiral galaxy hanging in plain sight, disguised as almost nothing by distance alone. And second, this, Andromeda, is the most distant object most people can see with the unaided eye. Stand under a truly dark sky. No telescope, nor binoculars, just the eyes you were born with. Find that faint smudge, and you are seeing across 2.5 million light-years, near the very limit of ordinary human vision. Almost everything else your bare eyes can find in the night sky lives inside our own galaxy, our own house. Andromeda is the great visible exception. One faint window cut into the wall of the sky, and through it, one other house is visible across the dark. With its porch light on, 2 houses, then 2 dinner plates in one quiet home, and a question rising softly between them. Is the space between the plates truly empty? 20 feet of nothing. 2.5 million light-years of nothing. The honest answer surprised even the astronomers who found it. And there is a second question, quieter still, that I will only whisper here and let wait. The 2 plates are not nailed down. One of them, measurably, is not where it used to be. Both questions have their chapters coming. The empty one comes first. The space between our galaxy and Andromeda looks, in every photograph ever taken, like pure black nothing. 2.5 million light-years of apparently perfect emptiness. And for a long time, that is more or less what astronomers assumed it was. A true void, a gap in the universe's furniture where nothing lived and nothing happened. The honest, modern answer is stranger and lovelier. The dark between galaxies is not empty. It is quiet. In a way, almost nothing else in nature is quiet. And the difference between empty and quiet is what this chapter is for. Start with the thinnest thing there is. Between the galaxies drifts a gas, mostly hydrogen, so sparse that it barely deserves the word gas at all. In the air you are breathing right now. Every cubic inch holds a number of molecules so large it has no everyday name. Trillions upon trillions of them. In the best laboratory vacuums humans have ever built, a cubic inch still holds many thousands of stray molecules. In the space between galaxies, the density falls to something like a single atom drifting in a volume the size of a large box. And in the deepest, emptiest stretches, far less than that. It is not one uniform thinness, either. It changes with where you are. Denser, along the great filaments that thread between galaxies, thicker still inside crowded clusters, and thinnest of all in the deep voids we will visit later. But everywhere out there, if you could stand in it, it would count as a perfect vacuum by any measurement your body could make. And yet, added up across distances measured in millions of light years, that almost nothing becomes enormous. Astronomers now believe that a very large share of all the ordinary matter in the universe, by many estimates, most of it, is not locked inside stars and the bright, visible bodies of galaxies at all. It is out there, spread thin as breath across the gulfs between them. The galaxies are not the universe, with some gaps in between. The galaxies are the bright exceptions, floating in an ocean of near invisible thinness that, in total, outweighs them. Let that inversion simply sit nearby. The light is the exception. The quiet is the rule. Now something warmer, and it is the part of this chapter I most want to give you. There are stars out there, not in galaxies. Between them, astronomers call them by several names: rogue stars, intergalactic stars, orphan stars. And their existence is not speculation. Beginning in the 1990s, observations with the Hubble Space Telescope found evidence of stars adrift in the spaces between the galaxies of the Virgo cluster, and later studies of a faint, diffuse glow called intracluster light, starlight rising from regions where no galaxy sits, confirm that great gatherings of galaxies are gently haunted by large populations of stars that belong to no galaxy at all. The counting is genuinely hard, and estimates vary, but in some clusters, the stray light between the galaxies appears to amount to a meaningful fraction of all the starlight there is. How does a star end up alone in the dark between galaxies? Almost always by accident of gravity. When galaxies pass close to each other, or merge, the tides of the encounter can sling stars outward, the way a hard turn slides loose objects across the back seat of a car. The star is not destroyed. Nothing dramatic happens to it at all. It simply leaves, possibly carrying some of its planets along with it, and sails out into the intergalactic quiet on a path that will never bring it home. Picture, purely as a thought experiment, a hypothetical world orbiting one of those orphan stars, far enough from any galaxy that the space around it is truly deep. Its sun still rises there. Its sky still turns. But its night sky holds almost nothing. Where our night is crowded with thousands of visible points of light, all of them neighbors inside our shared galaxy. That sky would be almost perfectly black to the unaided eye, marked only by a scattering of faint smudges. And each smudge would be an entire galaxy, seen whole, from outside. Any inhabitants of such a world, if such a world ever holds inhabitants, would learn about galaxies before they learned about stars. Their isolation would come with one strange gift: a cleaner view of the universe's true architecture than we have ever had from inside our own bright and dusty spiral. Nothing in this countryside moves quickly. Whole centuries can pass out there between one small event and the next, and the view holds steady the entire time. Like a landscape painting that happens to be real. There is a third resident of the dark worth meeting, and it arrives with tonight's usual honesty. When astronomers weigh the universe, using the way gravity bends, passing light, and steers the motions of galaxies, the numbers keep insisting that something massive is present beyond the thin gas and the wandering stars. Something that neither shines nor blocks light. Astronomers call it dark matter, and its honest status is this: its gravitational effects are measured, repeated, and about as solid as anything in modern astronomy. Its identity, what it actually is, remains genuinely unknown, one of the great open questions in all of science. And it is not spread evenly through the dark like fog. The evidence points to dark matter gathering into enormous halos around galaxies, vast, invisible envelopes far wider than the visible starlight, and into still larger structures threading through groups and clusters. Our Milky Way, on this picture, sits inside such a halo, the way a lit town sits inside its own wide, unlit countryside. Tonight we do not need to solve what the halo is made of, and neither does anyone else before morning. We only need to know that the dark between galaxies has weight as well as resonance. And later tonight, when we look at the universe's largest patterns, that hidden weight will turn out to be the quiet architect of nearly everything. So let the picture of this chapter assemble itself, one layer over another. The gulf between the Milky Way and Andromeda, that apparently blank black gap, actually holds an ocean of hydrogen thinner than any vacuum we can build. A scattering of exiled stars sailing through permanent night, and an unseen scaffolding of mass we have weighed but never identified. The emptiness is not empty. It is a countryside, sparse, dark, and calm, but a countryside all the same, lying between the bright towns. And the moment you start thinking of galaxies as towns in a dark countryside, a new question arrives on its own, gently, the way questions do at this hour. Towns are rarely alone. They gather, they form counties, and regions with names, and roads of a kind between them. Do galaxies do the same? They do. Our own galaxy is a member of a small gathering, a quiet town of galaxies with a plain and honest name. And it is time we took a slow walk through it and met the neighbors properly. Astronomers, who often reach for Greek and Latin when naming the heavens, named our own corner of the universe with almost comical plainness. It is called the local group. That is the official term, popularized by Edwin Hubble himself in the 1930s, and there has always been something restful in its modesty. The grandest structures get grand names. Home just gets called home. The local group is the gathering of galaxies bound together by gravity in our immediate corner of the universe. And its full membership list surprises almost everyone who hears it. Most people, if they know of any galaxies at all, know too. Ours and Andromeda. The real tally of known and likely members now stands at roughly 100 galaxies, with new faint ones still being discovered as surveys improve, and the honest expectation that more remain unfound. Our town is far bigger than its two famous residents, and most of its citizens are almost invisible. The names on the tour do not need keeping. Only the shape of the town matters tonight. The town is built around two large anchors. The Milky Way and Andromeda are the great spirals, by far the most massive members, and everything else in the local group is arranged around their gravity, the way a small town arranges itself around its two largest buildings. There is one middle-sized galaxy as well, the Triangulum Galaxy, a lovely loose spiral, roughly 3 million light-years from us, generally counted as the third largest member and likely bound in a long, slow relationship with Andromeda. After those three, the membership falls off quickly in size, down into the town's true population, the dwarfs. Dwarf galaxies are exactly what the name suggests. Small galaxies, some holding a few billion stars, many holding far fewer, and some so faint and sparse that they hold only a few 100,000 stars scattered across thousands of light-years. Barely more than a rumor of a galaxy. They are, as far as current surveys can tell, the most common type of galaxy in the universe, and our town is full of them. They orbit the two great spirals, the way moons orbit planets. Dozens of known satellites around the Milky Way. Dozens more around Andromeda. Each one a genuine galaxy with its own history, its own stars being born and dying, its own darkness between its suns. Two of them deserve a slow moment, because if you have ever stood under a southern sky, you have already seen them with your bare eyes. The large Magellanic Cloud and the small Magellanic Cloud hang in the far southern night like two detached wisps of the Milky Way, softly glowing patches that sailors and southern peoples have known since long before written history. They are our galaxy's most famous companions. Dwarf galaxies, roughly 160,000 and 200,000 light-years away, close enough to be gravitationally entangled with us, trailing a long streamer of gas behind them as they move. For the peoples of the southern hemisphere, other galaxies were never a discovery at all. They were simply part of the night, hanging there all along, waiting patiently for the rest of the world to learn what they were. Now, let us measure the town itself. From one side to the other, the local group spans roughly 10 million light-years, with the two great spirals sitting about 2.5 million light-years apart near its heart. Bring back the dinner plates one last time. If the Milky Way is a plate on your kitchen table, Andromeda is a plate about 20 feet away. Triangulum is a saucer somewhere near it, and scattered through the house. On shelves and windowsills and floors are dozens upon dozens of coins, buttons, and grains of rice. The dwarfs, the true population of the town, that is, the local group. One house, 2 plates, and 100 small quiet things, all falling slowly through the dark together, held by nothing but each other's gravity. And now, the turn this entire chapter has been walking toward, the one I asked you to hold loosely 2 chapters ago. Set the 2 scales side by side and feel the difference between them. Stars, measured against their own size, are absurdly far apart. Grapefruits separated by most of a country, tens of millions of their own widths from their nearest neighbors. This is why, in the entire Milky Way, with its hundreds of billions of stars all orbiting and drifting for billions of years, direct collisions between 2 ordinary stars are so rare that astronomers treat them as freak events. The gaps are simply too enormous. Stars almost never touch. Galaxies are the opposite, a few dozen of their own widths apart. Dinner plates in one shared house. and all of them moving, drawn endlessly toward each other by gravity across gaps that are, proportionally, almost nothing, which leads to a conclusion that sounds impossible the first time you hear it, and is nonetheless a plain fact of the universe. Galaxies collide. Galaxy encounters and mergers are common across cosmic history, especially inside groups like our own. Astronomers photograph them in every direction they look. Great spirals caught mid-embrace, their arms stretched into glowing streamers, their shapes folding into one another across hundreds of millions of years. Collisions are not a disaster that occasionally befalls a galaxy. They are, in large part, how galaxies grow. Our own Milky Way, the evidence strongly suggests, was assembled from smaller galaxies merging over billions of years, and it is quietly pulling apart at least one small dwarf galaxy at this very moment, stretching it into a stream of stars that wraps around our sky. So let the two facts rest side by side. Light as they are, stars almost never collide. Galaxies, given enough time and the right neighborhood, very often do. And if that is true, a very natural, very human question rises out of the quiet. The one I whispered at the end of the Andromeda chapter. The two plates in our house are not nailed down. One of them has been measured for over a century now, and the measurement keeps saying the same thing. What about us? What about our plate and the plate across the room? The answer is one of the best stories in modern astronomy, because science itself recently changed its mind about the ending. That story is next, and you have nothing at all to brace for. The story of our galaxy's future is one that science has recently rewritten in public, carefully, and the rewriting is the best part. So let us take it from the beginning. Start with what is measured and not in doubt. Andromeda is moving toward us. Astronomers have known this for over a century, since around 1912, when an astronomer named Vesto Slipher measured the light of the Great Spiral and found it shifted toward the blue, the unmistakable signature of an object approaching. The current approach speed is roughly 100 kilometers per second, about 250,000 miles per hour. The gap of 2.5 million light-years is closing. Tonight, while you drift, here, inside our bound little neighborhood, local gravity outweighs everything else in the story. And the most famous distance in our sky is a distance that is shrinking. For decades, that measurement grew into one of the most famous predictions in astronomy. The two great spirals, it was said, would collide in about 4 to 5 billion years, merge over the ages that followed, and settle into a single, enormous, elliptical galaxy. Writers even gave the future combined galaxy an affectionate nickname, Milkomeda. Textbooks printed it. Documentaries animated it. The collision was treated, for a generation, as an appointment already written into the sky. And then, quite recently, careful science did the thing careful science is supposed to do. It checked its own certainty, and the certainty softened. In June of 2025, a team led by the astronomer Till Sawala at the University of Helsinki, working with colleagues at Durham University in England and the University of Toulouse in France, published a study in the journal Nature Astronomy that re-examined the whole question using the newest data from two great observatories, the Hubble Space Telescope and the European Gaia mission. Instead of assuming the most likely value for every quantity, they did something more honest. They folded in the uncertainties. All of them. 22 separate variables, including the gravitational tug of the other significant members of our local group, the Triangulum Galaxy and the Large Magellanic Cloud. Then they ran 100,000 simulations of the next 10 billion years and simply counted the outcomes. The results arrived gently, which is fitting. In roughly half of those simulated futures, the two galaxies have a close encounter that eventually leads to a merger, most often not in 5 billion years, but in something closer to 7 or 8 billion. Usually after a near miss or two, the two spirals swinging past each other, shedding momentum, and falling back together in a slow spiral embrace. In most of the other half of the futures, they glide past each other at a wide enough distance that both galaxies continue on, largely undisturbed, for an extremely long time. The chance of a close encounter leading to a merger within the next 5 billion years, the version every textbook printed, came out at only about 2%. The fate of our galaxy, in the team's own words, is still completely open. What was an appointment has become a coin toss, stretched across 10 billion years, waiting on better measurements that are already underway. I find that more restful than the old certainty, and I suspect you might too. There is something quietly reassuring about a science that would rather admit a coin toss than defend a false appointment. But let us be honest about the other half of the coin, because even if the merger happens, it is not what the word collision makes you picture. And here is the second gift of this chapter. Remember the two scales you now carry. Galaxies are dinner plates in the same house. So they meet, but the stars inside them are grapefruits separated by most of a country. So when two galaxies pass through each other, and they genuinely do pass through each other, the stars almost entirely miss. The gaps between stars are so vast, compared with the stars themselves, that two galaxies can interpenetrate completely. Hundreds of billions of stars gliding through hundreds of billions of stars, with essentially no two stars ever touching. Astronomers who model such mergers expect direct stellar collisions to be somewhere between vanishingly rare and absent altogether. What actually collides is geometry and gravity. The two spiral shapes would be pulled apart over hundreds of millions of years, arms stretched into long glowing streamers, gas clouds compressed until they bloom with new star formation, and eventually, over billions of years, the whole combined system would settle into one calm, elliptical cloud of ancient suns. If anyone was standing on a planet inside it, there would be no crash, no sound, no single dramatic day. The merger of two galaxies, experienced from within, would be a slow rearrangement of the constellations, unfolding over spans of time so long that no single lifetime, no single civilization, could ever perceive it as an event. The sky would simply, across 100 million generations, become a different sky. One more honest note, resting lightly. The same research found that a smaller merger is actually more likely and sooner. Our galaxy's largest companion, the Large Magellanic Cloud, that soft glowing patch in the southern night, has a real chance of merging into the Milky Way within about 2 billion years. Even that, for anyone living here, would be gentleness itself. A small galaxy folding quietly into a large one, star by star. with room to spare between every pair of suns. So let the whole chapter settle into one thought. The most violent-sounding event in our galaxy's future is either much further away than we long believed, or may not happen at all. And even if it does, it will be the softest, enormous thing imaginable. A merger in which almost nothing collides. The sun, for what it is worth, will have lived out its own quiet story long before any of it unfolds. Nothing in tonight's sky is bracing for impact. The appointment book of the universe, on this page at least, is written in pencil, and the hand holding the pencil is patient beyond all measure. Now, having measured our house, our nearest neighbour, the countryside between them, and the odds of the two ever meeting, it is time for the largest step we have taken yet. Because our local group, our whole town of 100 galaxies, is itself just one small town, and the countryside does not go on forever in every direction unmarked. Somewhere out there, the towns gather. Somewhere out there is a city, and it is close enough that its gravity reaches all the way into our house. Meeting it is where we go next. To feel the next scale of the universe, we need to leave home for real this time. So let us do it slowly, the way everything worth doing tonight is done. Rise up out of your room, through the roof, through the atmosphere, and keep going. Watch the Earth shrink to a marble, the solar system to a bright point, and keep going. Watch the Milky Way spread beneath you into its full spiral, 100,000 light years of slow silver rotation, and keep going. Farther than any machine we have ever built will travel in the lifetime of our species. From a few million light years up, the whole local group finally fits in your view. 2 bright spirals, 1 smaller third, and 100 faint dwarfs, all drifting through the dark like a handful of lanterns scattered across a valley at night. Hold still at that height, and look outward, in every direction. The dark is not endless. Other lantern clusters glow in the distance. Other small towns of galaxies. Other groups, much like ours. Scattered across the black at distances of millions and tens of millions of light years. Our local group is not alone, and it never was. It is one village in a countryside full of villages, and in one particular direction. The villages become more frequent, the lanterns more crowded, until they gather into something that deserves an entirely different word. Not a town, a city. That city is called the Virgo cluster, and it sits roughly 55 to 65 million light years away, in the direction of the constellation Virgo as seen from Earth. The exact figure, depending on how the sprawling cluster's center is defined and which of its residents you measure to, let the ruler do its quiet work on that range. Andromeda cost us 2.5 million years of light travel, and that was one neighbor. Virgo is more than 20 times farther. The light arriving from it tonight left around 60 million years ago, give or take, when the Earth it would eventually reach had no ice caps. Palm trees grew near the poles, and the ancestors of whales were still walking on 4 legs at the water's edge. That is one delivery time, for one beam of light, from the nearest great city of galaxies. We are only looking. The city asks nothing of us, and it never has. And what a city it is, where our local group holds about 100 galaxies, most of them faint dwarfs. The Virgo cluster holds well over 1,000 known galaxies, by many catalogues more. gathered into a region not vastly wider than our whole local group. Great spirals, glowing ellipticals, dwarfs beyond counting, all swarming in shared orbit around their common center of gravity, moving at speeds of hundreds of kilometers per second. A slow-motion swarm of entire galaxies. At its heart sits one of the grandest single objects in our corner of the universe, a giant elliptical galaxy called Messier 87, a vast ball of ancient stars far more massive than our Milky Way. You may have seen its heart without knowing it. In 2019, when astronomers of the Event Horizon Telescope project released the first image ever taken of a black hole, that glowing orange ring that circled the world's front pages. The black hole in the picture was the central black hole of Messier 87, a giant holding billions of times the mass of our Sun, photographed across tens of millions of light-years of intergalactic dark, the first black hole humanity ever saw lives downtown, in the city nearest to our village. Here is the fact that turns this chapter from sightseeing into something deeper. The great mass of that city reaches us. Gravity never fully lets go across any distance. And the combined weight of more than 1,000 galaxies, plus all the unseen mass gathered among them, contributes to a slow gravitational flow in our whole corner of the universe. Our local group's motion through space measurably bends toward that crowded region of sky. Though honesty asks for the fuller sentence, Virgo is one contributor among many, and our drift reflects the pull of a much broader distribution of matter around us, including concentrations far beyond Virgo itself, one of which astronomers long ago nicknamed the Great Attractor. Think of it less as one city pulling one village, and more as water finding the slope of a wide, invisible landscape. We are on that landscape. We have measured our own slow slide along it. Astronomers gave the wider neighborhood a fitting name, the Virgo cluster and the many smaller groups around it, ours included, are together called the local supercluster, or the Virgo supercluster, a gathering spanning something like 110 million light-years, a county of villages arranged around one great city. And even that is not the top of the map. In 2014, a team led by the astronomer R. Brent Tully at the University of Hawaii charted the motions of thousands of galaxies and found that our supercluster is itself only one wing of a still vaster pattern, a region they named Laniakea, a Hawaiian word meaning immense heaven. Laniakea, by their mapping, spans something like 500 million light-years and contains the mass of roughly 100,000 galaxies. Its streams of galaxies flowing gently, like water down a valley, toward that same distant gravitational focus. Two honest notes belong beside the beautiful name. Exactly where Laniakea ends and the next region begins is a matter of definition, still debated, and unlike our local group, Laniakea is not one single gravitationally bound object. It is a watershed drawn on a map of motion, a way of tracing which way the rivers of galaxies flow, not a fortress wall holding everything inside forever. So let this chapter close with the full address, spoken slowly, the way a child might write it in the front of a notebook. Your room, your town, your country, Earth, the solar system, the Milky Way, the local group, the Virgo supercluster, Laniakea. Each line of that address is enormously larger than the line before it. and every line of it is measured, mapped, and real. You had this full address all along. Tonight is simply the first time anyone read it to you in order. But notice something as you tuck that address away. A small unease worth keeping, because it is the thread the rest of tonight will pull. Every line of the address past our local group describes things that are not holding still. Flows, streams, watersheds. The map above a certain scale is not furniture. It moves. And there is a question we have not yet dared to ask about all that motion, about what the largest gaps on the map are quietly doing while the galaxies drift. Before we can ask it properly, we need to see the map itself, the whole pattern at once. And the story of how humans first drew that map begins with two astronomers in Massachusetts. A thin slice of the night sky measured one galaxy at a time, and a picture that emerged from their numbers looking, to everyone's astonishment, like a little stick figure waving back. That story, and the great empty spaces it revealed, is next. Every map we have drawn tonight has been a map of things. Stars, galaxies, towns, cities, the wide watershed of Laniakea. But an honest map of the universe is mostly not things. An honest map of the universe is mostly gaps. And the gaps have a name. Astronomers call them voids. And finding them was one of the great surprises of the 20th century, because almost nobody expected them to be there. Well into that century, the working assumption was that galaxies were sprinkled through space more or less evenly, like raisins through a well-mixed cake, mapping the universe in 3 dimensions, measuring not just where each galaxy sat on the sky, but how far away it was, seemed likely to confirm that smoothness. The first hints said otherwise. In 1981, the astronomer Robert Kirshner and his colleagues, measuring galaxy distances in the direction of the northern constellation Bootes, found something missing. In a region where they expected a rich scattering of galaxies, they found instead an immense rounded emptiness, now estimated at roughly 330 million light-years across. Say that slowly against our ruler. The entire gulf between the Milky Way and Andromeda would fit into the Bootes void more than 100 times over. A single, quiet hollow, wider than the distance from us to the Virgo cluster and back again, several times over. Then came the map that changed the picture for good. And it is one of the most charming stories in modern science. In the middle 1980s, at the Harvard-Smithsonian Center for Astrophysics, the astronomers Margaret Geller and John Huchra set out to survey a thin slice of the sky in depth, measuring distances to more than 1,000 galaxies, one by one, night after night. A project of enormous patience with no guarantee of an interesting result. Huchra did much of the observing. Geller and her students turned the measurements into a map, and when the slice was finally plotted, in 1986, the galaxies did not scatter like raisins at all. They lined up, they traced thin, curving walls and filaments, wrapped around enormous, rounded, empty spaces, and near the middle of the plot, by pure chance, the galaxies happened to arrange themselves into a shape so suggestive that nearly everyone who saw it described it the same way. It looked like a little stick figure, a small human form standing in the data with its arms open, as if the map were waving back at the people who drew it. Geller later described her own reaction plainly. She understood at once that nobody had expected this, and that the smooth universe of the textbooks was gone. A few years later, extending the survey, Geller and Hukra traced a single sheet of galaxies stretching at least 500 million light-years across their map. A structure so large they named it, with admirable directness, the Great Wall. 2 people, a mountaintop telescope, and a thin slice of sky. And the universe turned out to have architecture, bubbles and walls, hollows and films. Nobody had ordered that universe. It was simply the one that showed up in the data, waving. The decades since have only deepened the picture. Modern surveys have catalogued voids by the thousands, in every direction, with typical widths of tens to hundreds of millions of light-years. When astronomers add up the volume of the universe, the voids win, and it is not close. By most estimates, the majority of all space is void, with the galaxies, the clusters, the bright crowded cities of tonight's journey confined to the comparatively thin borders in between. The universe is not a cake with raisins. The universe is closer to a sponge, or a flamme, almost entirely open space, with its substance gathered into delicate walls around the holes. And the voids are not perfectly empty, which somehow makes them lovelier. Careful searches inside the boot's void have found some galaxies drifting there, a few dozen known, scattered through a volume that would ordinarily hold many thousands. The astronomer Greg Aldering, who studied the region, offered a comparison that has been quoted ever since, and it deserves to be heard at this hour. If our Milky Way had been located at the center of the boot's void, he observed, we would not have known that other galaxies existed until the 1960s. Sit with what that means. The discovery Hubble made in 1923, the night the universe grew, would have been delayed by 40 years, simply because of where our home happened to sit. Every telescope humanity built before the space age would have swept the sky, found our own stars, and then passed them. Nothing bright enough to notice. An entire civilization's picture of reality, shaped not by its intelligence, but by its address. Now let us do the one thing this chapter was truly built for. Let us stand in the middle of one. Picture yourself, gently, at the center of a great void, hundreds of millions of light years from the nearest bright galaxy in any direction. There is no danger here. There is, in fact, less happening here than anywhere you have ever been. Look around. The sky is black in a way no sky on Earth has ever been black. No stars. Because you are inside no galaxy. No visible smudges. Because even the nearest great galaxies are too far now for an unaided eye to find. The only warmth the place possesses is the faint ancient glow that fills all of space. The leftover radiation of the early universe, humming along at just a few degrees above absolute zero. A background so gentle that no skin could ever feel it. An atom drifts past. And then, for a very long time, nothing else does. Whole years pass. Whole centuries. The view does not change. Nothing arrives, because everything that exists is far away, minding its own bright business elsewhere. And here is the strange mercy of the place. The reason I brought you here at this hour, nothing in a void is wrong. Nothing is missing that was supposed to be there. Nothing waits, or worries, or hurries. It is simply the universe at rest. the deep default calm, out of which the bright and busy places are the rare exception. Most of everything, it turns out, is this: quiet, dark, unhurried, and utterly at peace. If the universe has a resting heart rate, you have just floated in it. But do not let the voids convince you the universe is shapeless, because the stick figure in Geller and Hukra's map was trying to tell us the opposite. The voids are not scattered randomly, like holes punched anywhere in a sheet. They are arranged. The galaxies wrap around them in continuous walls and threads. Void beside void beside void, like the cells of a vast foam. Zoom out far enough, past Laniakea, past every structure we have named tonight, and the walls and threads and hollows resolve into one single pattern, the largest coherent pattern anyone has ever mapped. The shape the universe makes when nothing is left out of the picture. Astronomers call it the cosmic web, and it is time we finally looked at the whole thing. Every journey outward has a final zoom, a scale where the whole picture is at last in the frame. And tonight we have reached it. So, take the slowest breath of the night, if it wants to be taken, and let us look at everything. Picture the view assembling itself the way it actually assembled in humanity's real maps. The slice Geller and Hukra drew in the 1980s was the first honest glimpse, a thin wedge of bubbles and walls. Then the projects grew, beginning in earnest in the 2000s. Surveys, like the Sloan Digital Sky Survey in New Mexico, measured the positions and distances of first hundreds of thousands, then millions of galaxies. Each measurement, one dot of light placed carefully into a three-dimensional map. No single person planned the shape that emerged. The dots simply fell where the universe put them, and, as the dots accumulated, decade after decade, the shape rose out of the data like a photograph developing in its tray. The galaxies of the universe are arranged in threads, long, luminous filaments, each one a chain of galaxies and groups and clusters strung together across hundreds of millions of light years, threading through the dark like glowing fibers. Where filaments meet, they knot into the great clusters. The bright crowded cities like Virgo, sitting at the intersections like towns built where highways cross. Between the threads stretch broad sheets and walls of galaxies, and enclosed by the walls sit the voids, the vast calm hollows we just floated through, cell after cell after cell, threads, knots, walls, and hollows, repeating in every direction, at every distance our surveys have reached. That is the cosmic web, the largest mapped pattern in existence. It is worth being precise about what it is, because precision here makes it stranger, not duller. The web is not one object, the way a galaxy is an object. It is the grand arrangement of all the objects, the pattern of everything, and on scales even larger than the web's own cells. The universe finally begins to look statistically smooth, the same kind of pattern repeating without new surprises, like a fabric whose weave you have finally seen up close. You live inside one of its threads, in a small town near a great city, at a modest intersection of the largest pattern there is. Two comparisons arrive on their own the moment anyone sees the map, and both are honest enough to share. The first is foam, the structure of soap bubbles or the inside of a loaf of bread. Thin, shining walls around empty cells. The second comparison is the one that tends to stop people mid-sentence. Images of the cosmic web look strikingly similar to images of the network of neurons in a brain. Threads and knots and branching connections. Let me be careful here. In keeping with tonight's promise, the resemblance is visual, not literal. The universe is not a brain. No serious scientist claims it thinks. And the two structures are built by entirely different processes that happen, sometimes, to produce visually similar networks. What is true, and gentler, is that nature has a limited wardrobe of shapes for spreading things through space. And this is one of its favorites. You are built from one of nature's recurring patterns, and you live inside another instance of it, grown 500 million times larger by completely different means. Now the question the whole chapter has been holding, the one worth carrying gently towards sleep. Where did the web come from? Who arranged the threads? The honest answer is one of the most quietly astonishing findings in all of science. The web was drawn before there were stars, in the very first moments of the universe. And the pencil was almost unimaginably small. In the extremely early universe, according to our best supported picture, all of space was filled with hot matter, spread almost perfectly evenly. But not exactly perfectly. There were tiny irregularities, minuscule flickers of density, believed to have begun as quantum fluctuations, the restless trembling that physics finds at the smallest scales of reality, stretched enormously as the young universe expanded. Some regions ended up with the faintest whisper more matter than average. Some ended up with a whisper less. The difference was tiny, parts in 100,000. A smoothness far more perfect than any surface humans have ever manufactured. But gravity is patient, and gravity never forgets an advantage. A region with slightly more matter pulled slightly harder, gathered slightly more, and so pulled harder still, over thousands, then millions, then billions of years. The whispers grew into seeds, the seeds into knots, the knots into the first galaxies, and the flows of matter falling toward those knots stretched naturally into threads. Meanwhile, the regions born with a whisper less lost their matter to their luckier neighbors, emptying gradually into the voids. The unseen mass we met in the dark countryside. The dark matter gathered in halos and larger structures, did most of the early gathering, forming the web's hidden skeleton first, with ordinary matter, the stuff of stars and of you, flowing afterward into the pattern it laid down. And the crucial point is that this story can be checked. The infant universe left behind a portrait of itself, that same faint glow we felt in the void, the cosmic microwave background. When satellites mapped that glow in exquisite detail through the 2000s and 2010s, the tiny flickers were there, at just the right strength, in just the right pattern, to grow into the web our Galaxy surveys photograph today. The beginning and the end of the story match. We have baby pictures, and the baby grew into the sky. Let that settle as softly as it wants to. Every thread of galaxies, every great city, every calm hollow, our local group, our address, this room, all of it traces back to microscopic trembles in the first sliver of the first second, magnified by nothing but gravity and time. The largest pattern in existence is the enlargement of the smallest fluctuation there has ever been. Nothing about you required a different origin. You are a very patient echo of a very small ripple. And here, at the very top of the map, with everything finally laid out below us, comes the turn that the entire second half of tonight belongs to, because I have let you assume, for most of this evening, one small comforting thing that is not quite true. I have let you look at this map as if it were finished, as if the threads and voids were furniture, arranged and staying put. They are not staying put. The map is in motion. And not only the gentle local drifting we have already met, out beyond everything bound to us. The great distances are becoming longer, not because anything is travelling, but because of something far stranger, something discovered by the same Edwin Hubble we met on a mountaintop, in the years just after he proved the galaxies were real. The space itself, between the threads of the web, is stretching. That discovery, what it truly means, and what it does not mean, is where we go next. Let us return, one last time, to the man on the mountaintop, because Edwin Hubble was not finished changing the universe. And his second discovery is the reason tonight's journey has the title it has. The scene is the same: Mount Wilson, above Los Angeles, the 100-inch Hooker telescope. In the late 1920s, Hubble had already proven the galaxies were real, distant islands of stars. Now he set about combining two kinds of measurement, and honesty asks us to introduce both of their owners. The first kind was distance, his own hard-won specialty, built on Leavitt's ruler. The second kind was speed, and much of that data belonged to others. Above all, to Vesto Slipher, the quiet, meticulous observer at Lowell Observatory in Arizona, who had spent years measuring the light of the spiral smudges, and to Milton Humason at Mount Wilson, a remarkable man who had begun his career at the observatory as a mule driver and janitor before working his way, without a college degree, into becoming one of the finest observational astronomers alive, extending the speed measurements to ever fainter galaxies. The tool for measuring speed already existed. When an object moves away from you, the light it sends is stretched, its waves lengthened, shifted toward the red end of the spectrum, the same physics that lowers the pitch of a siren after it passes you on the street. Astronomers call it redshift, and Slipher's patient years of work had already revealed something odd. Andromeda aside, almost every spiral he measured was shifted red. Almost everything, in every direction, seemed to be receding. Hubble combined his distances with those speeds, and in 1929 he published a short paper containing one of the most consequential graphs ever drawn. On one axis, the distance to each galaxy; on the other, its speed away from us. And the points did not scatter randomly. They fell along a line. The farther a galaxy was, the faster it was receding, in direct proportion. Twice as far meant twice as fast. 10 times as far, 10 times as fast. Distant galaxies, in every direction, obeying the same simple rule, as if the whole universe had agreed on it in advance. The first interpretation everyone reaches for is wrong in a beautiful way. So, let us take the step carefully. The first thought is always the same. If everything is rushing away from us, we must be at the center of some great explosion. with the galaxies flying outward through space like shrapnel. But that is not what the mathematics says. The galaxies are not flying through space away from a center. The space between the galaxies is itself expanding. There is a difference, and it changes everything. Here is the picture astronomers actually use, and it is homely enough for this hour. Imagine a loaf of raisin bread rising in a warm oven. The raisins are galaxies. The dough is space. As the dough expands, every raisin moves away from every other raisin. Not because any raisin is swimming through the dough, but because the dough between them is growing. And notice the elegant part. From the point of view of any single raisin, all the other raisins are receding, and the distant ones recede fastest, because there is more expanding dough between them. Every raisin sees the same pattern. Every raisin feels like the center. In the standard picture of cosmology, that is precisely the point. The expansion has no central location within space at all. It is not happening away from somewhere. It is happening everywhere, evenly. One correction to the loaf, and it is the correction this whole night has been preparing you to appreciate. Not every raisin drifts apart. Where raisins are clumped tightly together, held by their own gravity, they simply do not separate as the loaf rises. Their little bound cluster stays exactly as it is, while the growth shows up only in the wide dough between the clumps. That is our situation. The local group is such a clump of raisins, held by its own gravity, which is why the most famous nearby distance in our sky is the great exception to Hubble's rule. Andromeda is not receding. Local gravity is still drawing it and our galaxy gently toward each other, exactly as we measured 5 chapters ago. The stretching belongs to the great distances, the wide gaps between the threads of the web, the widths of the voids, and it becomes truly measurable only across the vast, unbound stretches of the cosmos. Our own small neighborhood, bound and huddled, holds its shape. There is a name that belongs beside Hubble's here. In the interest of tonight's honesty, 2 years before Hubble's famous paper, in 1927, a Belgian physicist named Georges Lemaitre, F., who was also a Catholic priest, had worked out from Einstein's equations that the universe should be expanding, and had derived essentially the same law from the data available to him, publishing in a journal so obscure that the world largely missed it. Lemaitre then followed the logic backward and asked the question the expansion begs. If everything is growing apart, then, long ago, everything was closer together, and at the beginning, unimaginably close. He called his idea the primeval atom. The world came to call it the Big Bang. In 2018, nearly a century later, the International Astronomical Union voted to rename the expansion rule the Hubble-Lemaitre law, restoring the quiet priest to his place beside the famous American. Science, at its best, eventually pays its debts. Even Einstein has a small confession in this story, told softly. When he first applied his equations of gravity to the whole universe, in 1917, the equations tried to tell him the universe could not sit still. It had to expand or contract, trusting the ageless, unchanging cosmos everyone then believed in. Einstein added an extra term to his own equations to hold the universe motionless. A mathematical prop, a stabilizer. After Hubble's discovery, Einstein visited Mount Wilson in 1931, looked through the Great Telescope, and accepted the expansion. According to the physicist George Gamow, Einstein privately called that added term the biggest blunder of his life. Hold onto that abandoned term. Gently, it is not done with us. Later tonight, in one of the strangest turns in the history of physics, it comes back. So here is where the chapter leaves you, and it is the thought the whole video was named for. Out beyond our bound neighborhood, the map is not furniture. The map is swelling, the wide gulfs between the threads of the web, the widths of the great voids, the road to Virgo and beyond. All of it is quietly lengthening. Tonight, while you rest, at no cost and no risk to anything bound and close. Nothing is fleeing. Nothing is exploding. The universe is simply out in its widest places, becoming more, and now your own mind, if it is still following, has probably found the question hiding in Hubble's simple line, the question that makes the next chapter necessary. If a galaxy twice as far recedes twice as fast, and the universe goes on and on, then somewhere out there, at some enormous distance, the numbers must climb to something impossible. Somewhere, the expansion itself must exceed the speed of light. Surely that cannot happen. Surely Einstein forbids it. The answer is that it happens. It is happening now, and understanding why it is allowed is one of the deepest pieces of calm the universe has to offer. The rule you learned, the one everyone learns, says that nothing can travel faster than light. And the rule is true. Nothing can. No object, no signal, no spacecraft, no message will ever move through space, past its neighbors, faster than a beam of light. Einstein's speed limit has been tested for over a century, and it has never once bent. And yet, at this moment, there are galaxies whose distance from us is growing faster than the speed of light. Both statements are true. The whole chapter lives in the space between them, and the space between them is gentler than it looks. Here is the resolution, and you already own every piece of it. Einstein's limit is a local law. It governs objects and signals passing one another through nearby space. And there it is absolute. What it does not govern is the slow, global lengthening of enormous distances as the dough rises. The distant galaxies are not racing through the universe. They are sitting almost still in their own neighborhoods, tending their own stars, while the space between us and them grows. This kind of cosmic recession is a different measurement from local motion, and it carries no speed limit, because nothing is actually traveling. No object outruns light. The gap itself widens, silently, everywhere. And a widening gap is not a mover. It breaks no law. It carries no message. It simply adds more universe between 2 points. Now feel the consequence. Slowly, because it reshapes the meaning of every large distance we have named. If a galaxy is far enough away, the total stretch accumulating along the whole enormous path between us adds up to more than the speed of light. Astronomers can calculate where that threshold lies in the standard picture of cosmology. It is called the Hubble distance, and it sits, by current measurements, somewhere around 14 billion light-years away. Any galaxy beyond that line is receding from us. Right now, faster than light, and a vast number of the galaxies we observe already lie beyond that line. Their portraits fill our deep photographs, and yet the space between us and them is opening faster than any signal could ever chase. Nothing about this is a threat. It is simply the truth arriving at its full size, and the truth has room in it for us, as you are about to see. Because now comes the question that matters, the human one. If a galaxy is receding faster than light, can we still see it? And could we ever, even in principle, reach it, or touch it, or say anything to it? The seeing, wonderfully, is yes. For many of them, light those galaxies released long ago is already deep inside our region of space, swimming toward us through dough that rises more slowly nearby. And so it still arrives, ancient and stretched and red, but real. Some of the light landing in our telescopes tonight left galaxies that were receding faster than light, both then and now. The universe is generous with its past. The future is a different matter, and this is the heart of the chapter. Because the expansion continues, and, as the next chapter will show, appears to be quickening. The standard picture implies a distance beyond which no message we send tonight will ever arrive, no matter how long it travels. A beam of light launched from Earth this very evening, aimed at a sufficiently distant galaxy, would fly at the fastest speed the universe allows, forever, and lose. The gap ahead of it would grow faster than the beam could cross it, endlessly, like a walker on a path that lengthens 2 steps for every step taken. Astronomers call that boundary the cosmic event horizon. Current calculations, within the standard model of cosmology, place it at a distance of roughly 16 billion light-years. Galaxies beyond that horizon are, on that picture, permanently out of reach. Not difficult to reach, not awaiting better engines. Out of reach in principle, for anything, including light itself. Let me say the strangest part plainly, because at this hour it deserves plain words. There are galaxies we can see tonight, whose ancient light is entering our telescopes at this very moment, to which we can never reply. Their portrait hangs in our sky. Any message we send them will travel forever and never arrive. The universe is full of one-way windows, places through which the past can reach us, but through which nothing of ours can ever reach back. And with every passing year, more distant galaxies become permanently unable to exchange any newly sent signal with us, slipping quietly into that same category of visible but unanswerable. I promised you at the start of tonight that this would end in peace, not dread. So let me show you where the peace in this actually lives. Nothing is lost when a galaxy passes beyond that horizon. No star goes out. No world ends. The galaxy continues, exactly as before, its suns rising over its own countless quiet mornings. What ends is only the possibility of contact. And contact was never occurring anyway. The horizon takes nothing from anyone. It simply makes official what the distances had already decided. And notice what it does to the meaning of everything within reach. Our local group is bound by gravity. And in the standard cosmological picture, cosmic expansion does not pull apart systems that are already gravitationally bound. Everyone we could ever truly reach, cosmically speaking, is already in the room with us. The universe has drawn a wide circle around what can be touched. And for as far into the future as our current physics can reliably describe, what is inside the circle stays gathered. One honest note before this chapter lets you go. Spoken the way careful people speak. The exact placement of these horizons depends on how the expansion behaves across the deep future. And that depends on the nature of whatever is driving it, which remains, as we are about to see, genuinely and openly uncertain. The numbers I have given you, 14 billion, 16 billion, are our best current calculations inside our best current model, not commandments. The shape of the story, the one-way windows, the growing quiet, the bound and gathered town. That shape is as solid as anything in modern cosmology, and it is the shape, not the digits, worth falling asleep with, which leaves only the deepest question of the night still standing. Twice now I have said the expansion appears to be quickening. That single word is one of the most surprising discoveries in the history of science. It was made in the late 1990s by two rival teams racing to measure the universe with exploding stars. Both teams expecting to find the expansion slowing down, and both finding, to their open disbelief, the opposite. Something is pressing the accelerator. Nobody has ever seen it. Its story is next, whenever you are ready, and there is no hurry at all. The story of dark energy begins with two teams of astronomers who set out, in the 1990s, to measure how fast the universe was slowing down, and it ends, for now, with one of the most honest sentences in modern science. We do not know what most of the universe is made of. Everything in between is worth telling slowly. The logic the two teams carried into the work was simple and sensible. The universe is expanding, and the universe is full of matter. And matter pulls on matter. Gravity, across billions of years, should therefore be acting as a brake, gradually slowing the expansion, the way Earth's gravity slows a ball thrown upward. The question of the age was not whether the expansion was slowing, it was by how much, because the answer would reveal the universe's ultimate fate, whether it would expand forever, ever more slowly, or someday halt and fall back inward, to time the universe. Both teams used the same remarkable tool, a kind of exploding star called a Type 1, a supernova. These explosions have a property astronomers treasure. They are not all identical in brightness, but they are consistent enough that their light can be carefully calibrated, the exact shape and color of each fading explosion revealing how bright it truly was. That makes them what astronomers call standardizable candles. Close cousins of the standard candles, Henrietta Leavitt's pulsing stars, gave Hubble, but visible across billions of light years instead of millions. Find one in a distant galaxy, calibrate its light, compare its true brightness with how faint it appears, and the distance falls out. Combine that with the galaxy's redshift, and you can read the history of the expansion itself, written in ancient light. Two rival teams raced to do it. The Supernova Cosmology Project, led by Saul Perlmutter at Berkeley, and the High-Z Supernova Search Team, associated with Brian Schmidt in Australia and Adam Rees. Then, in California, the rivalry matters, and you will see why in a moment. Through the middle 1990s, both groups hunted supernovae across billions of light years, measured, calibrated, and remeasured. And in 1998 and 1999, both teams published their results separately and found the same impossible thing. After careful calibration, the distant supernovae were still too faint. They sat farther away than a slowing universe could have carried them. The expansion of the universe was not slowing down at all. It was speeding up. Feel how strange that is. At whatever pace suits you. It is a ball thrown upward that does not fall back, does not even coast, but climbs faster and faster, as if the sky itself were pulling it. Members of both teams have described their own disbelief openly. Reyes has recalled checking his calculations again and again, assuming error. Schmidt described his reaction as somewhere between amazement and horror. Nobody wanted this answer. And that is precisely why the rivalry matters. Two competing groups, using independent data, hoping, if anything, to prove each other wrong, arrived at the same result at the same time. In science, that is about as convincing as a surprise can get. In 2011, Perlmutter, Schmidt, and Rees shared the Nobel Prize in Physics for the discovery. Let us be precise, gently, about what was actually found, because the precision is part of the honesty. What is real and measured is the acceleration. The expansion of the universe is speeding up. That is the observation, confirmed now by several independent lines of evidence. What causes it remains unknown. Physicists needed a name for the unknown cause, and the name they chose tells you exactly how much they knew. Dark energy. Dark, as in unseen. Energy, as in something. It is a label on a mystery, not a description of a thing in hand. And when astronomers balance the universe's books using everything available, the ancient background light, the great galaxy maps, the supernova, the accounting comes out astonishing. All ordinary matter, every star, planet, gas cloud, and person, amounts to roughly 5% of the universe. Dark matter, the unseen scaffolding from earlier tonight, is about 27%, and dark energy, whatever it is, accounts for roughly 68%. The majority of the universe is the name of a question. Now, the return I promised you 2 chapters ago, and it is one of the finest ironies in the history of physics. When Einstein wanted to hold his universe still in 1917, he added a term to his equations, a uniform energy of space itself, then discarded it after Hubble's discovery, reportedly calling it his greatest blunder. Look again at what dark energy behaves like, at least in the simplest reading of the data. A uniform energy woven into space itself. Everywhere the same, pushing the expansion outward. It is Einstein's abandoned term. The cosmological constant, returned from the wastebasket as the leading candidate to explain 2/3 of the universe. Even his discarded ideas, it turned out, were better than most people's keepers. For years, the simplest story has been exactly this, that dark energy is a constant, a fixed property of every cubic inch of empty space, unchanging forever. But tonight's promise is honesty, and honesty requires the newest chapter of this story, which is still being written as you drift. In the 2020s, a new instrument in Arizona called the Dark Energy Spectroscopic Instrument, DESI for short, began building the largest 3-dimensional map of the universe ever made, using 5,000 small robots to aim optical fibers at galaxy after galaxy through the Mayol telescope at Kitt Peak. As of the middle of 2026, DESI has completed its planned survey, mapping more than 47 million galaxies and quasars, and its results so far contain a genuine surprise. When DESI's map is combined with the supernova data and the ancient background light, the analyses show a statistical preference, not yet a proof, for the idea that dark energy may not be constant after all, that its push may be weakening, evolving across cosmic time. The teams report the hints at a strength that intrigues but does not yet convince, and the first results from the full survey are expected to be analyzed over the following couple of years, with the search extended further to sharpen the answer. So, the truthful status, as this is written, is this: the acceleration is real and measured. The identity of the accelerator is unknown, and whether its pressure is eternal or slowly changing is an open question that may be settled within this decade by instruments working right now, under the same night sky you are resting beneath. Let that uncertainty lie lightly on you, because it should. Nothing about your night depends on it. But the far future of the distances, the deep fate of every gap we have crossed tonight, does depend on it. And that is where the journey goes next. Because if the acceleration continues, something extraordinary and strangely poignant happens to the sky itself. Over the deepest reaches of time, the universe, slowly, begins to close its own curtains. Let us go watch it happen, from a very safe distance, in the last long look outward of the night. Everything in this chapter takes place so far in the future that the numbers stop behaving like time and start behaving like poetry. And everything in it follows from one assumption, stated plainly at the door. If the acceleration continues, as the standard picture describes, this is what the deep future holds. Hold it the way you hold the end of a story you trust, loosely, and let us watch what the expansion slowly does to the sky. Begin with what we learned 2 chapters ago. There is a horizon, a distance beyond which the stretching of space outruns light itself, and galaxies that pass beyond it drift out of any possible future contact. Tonight, that horizon sits comfortably far away, and our sky is crowded with visible galaxies, hundreds of billions within reach of our instruments. But an accelerating universe does not stay generous. Across billions and tens of billions of years, more and more galaxies are carried beyond the horizon, their light stretched and dimmed and finally cut off from ever arriving fresh, one by one, at a pace no living thing could ever notice. The distant lamps of the universe are carried out of the theatre. Follow it forward, gently, in stages, some tens of billions of years from now, on the standard accelerating picture. The galaxies beyond our own neighborhood will have receded so far and so fast that their light fades beyond any practical detection. The great Virgo city, the threads of the cosmic web, the thousands of glittering clusters in every deep photograph humanity has ever taken. All of it dims, reddens, and slips away, given roughly 100 billion years. By the estimates of astronomers who study the deep future, the sky outside our own gravitationally bound home empties almost completely. The view beyond the neighborhood goes dark, not because the universe ended, but because the distance is finally won. And yet, remember the circle drawn around what can be touched, because here it becomes the heart of everything. The expansion is powerless against gravity at close range. Our local group, the Milky Way, Andromeda, and their 100 small companions, is bound, and bound systems are not pried apart by the rising dough. While the far universe recedes, our town keeps its own company over those same deep spans of time. The galaxies of the local group continue their slow gravitational dance with each other. And the coin toss we met earlier tonight finally resolves, one way or the other. If the Milky Way and Andromeda do eventually merge, as roughly half the simulations suggest, the town's two great spirals settle into a single vast elliptical galaxy, one enormous calm cloud of ancient suns. If they do not merge, they remain neighbors in the same bound household, circling their shared center of gravity while the rest of the universe fades from view. Either way, the essential picture holds. In the deep future of the Standard Model, everything that remains visible in the sky is home. One neighborhood, whether gathered into one galaxy or several, surrounded by darkness in every direction. Now comes the thought this chapter exists for, the one worth carrying carefully. Imagine astronomers arising on some world inside that far future neighborhood, 100 billion years from now, building their first telescopes, doing everything right. They sweep the sky and find their own galaxy's stars. And beyond them, nothing. No Andromeda smudge. No Virgo. No deep fields crowded with spirals. No cosmic web. Every observation would tell them, honestly and consistently, that the universe is one island of stars, floating in an infinite empty black. The expanding universe, the ancient background glow, by then stretched into undetectability. The whole story we spent tonight learning would be invisible to them, not hidden by their ignorance, erased by the distances themselves. They could be brilliant, careful, and completely wrong, and the evidence needed to correct them would simply no longer arrive anywhere in their sky. Scientists who write about this era, including the astrophysicists Lawrence Krauss and Robert Scherer, who explored it in detail in 2007, have drawn out its strange lesson. A universe can outlive the evidence of its own history. And now, turn that thought around, because it has been pointing at you all along. We are not the late astronomers. We are the early ones. We happen to exist in the era when the evidence is still on display, when Andromeda still hangs visible over autumn fields, when the web still glitters in our deep photographs, when the ancient background light still hums into our antennas, when the whole story is still readable in the sky. The window is enormous by human measures, billions of years wide, and it is still a window, and we are standing in it. Every fact you have heard tonight was, in a sense, mailed to us by a universe that will not always be able to send it. The night sky above your roof is not just beautiful. It is testimony with a timestamp, and ours is among the generations lucky enough to take the deposition. One honest breath before the chapter lets you go. All of this rests on the acceleration continuing as currently modeled, and as we learned in the last chapter, the newest measurements are actively probing whether dark energy's push is truly eternal or slowly changing. If it evolves, the deep future could soften or shift in ways not yet calculable. The far story I have told you is our best current projection, not a prophecy, and the scientists who drew it would be the first to say so. The near story, though, the one that matters tonight, is not uncertain at all. The lamps are lit, the sky is full, the evidence is arriving. Tonight, on schedule, through your window. So, we have followed the distances as far as they go, outward past every galaxy, and forward past every era. And there is only one destination left. The one every journey of this kind was always secretly headed toward. Home. The last chapter of tonight is about the room you are lying in, the small, warm center of every measurement we made, and what all those unthinkable distances, honestly reckoned, actually add up to for the person resting inside them. Come all the way back with me now, back down through everything we climbed, down through the deep future, past the long good night of the sky, down through the cosmic web, its threads and knots receding behind us, down past the great voids, holding their perfect silence, down through Laniakea's slow rivers, down the long road from Virgo, back into the small, familiar town of the local group, past Andromeda, hanging wider than the moon, into the slow silver wheel of the Milky Way, down one quiet spiral arm to one ordinary star, one small blue world, one roof, one room, one person, breathing slowly in the dark. Here, this is where every measurement tonight began, and this is where every one of them ends. I told you at the start that the distance between galaxies is worse than you think, and we have kept that promise honestly. The distances are wider than intuition can hold. They are mostly empty. The greatest of them are growing as you lie here, and some have already grown beyond the reach of anything we could ever send. All of that is true. And now, at the end, I want to show you what all of that truth adds up to, because it is not what the word worse suggests. Held up to the light, each fearsome fact of tonight turns out to have a gentle side, and this chapter is simply the turning. Start with the expansion itself, the great stretching that gives this video its title. Here is the fact almost no one tells you. It cannot touch you. The expansion is real out among the threads of the web. But here, at home, gravity governs. The forces binding your body together, the gravity holding you to the earth to the sun to the galaxy, and our galaxy to its neighbors. All of it overwhelms the cosmic stretching so completely that the expansion contributes nothing measurable to any distance in your life. In the standard cosmological picture, the expansion does not pull apart what is already bound, and everything you can name in your world is bound many times over. The gap between you and everything you love is not growing tonight. The universe stretches only where nothing is holding on. And here, everything is holding on. Feel where that leaves us. The universe has, in effect, drawn a boundary, outside it, across the widest places. The distances win. Inside it, gravity holds. And the inside is not small. The inside is the entire local group. 100 galaxies, trillions of stars, 10 million light years of bound and gathered home. And for as far into the future as our current physics can reliably describe, what is gathered stays gathered. The expansion is not scattering us. If anything, it has fenced the garden, and the garden is vast beyond imagining. and we are inside the fence. Take the emptiness next. All those millions of light years of near perfect quiet between the bright places. That emptiness is not a flaw in the universe. It is the peace of the universe. It is why the sky above your roof has held the same patient constellations through every night of your life. Why no collision, no chaos, no cosmic surprise has ever interrupted a single one of your evenings. The distances are the stillness. A crowded universe would be a loud one. Ours is spacious. And so Earth is calm. And the quiet you feel tonight is a small local copy of an enormous original. Take the one-way windows. The galaxies we can see but never answer. There is a genuine sorrow in them, and I will not pretend otherwise. But notice what they quietly underline. Everything that could ever truly be reached, everything answerable, is already inside the circle. Most of it inside this one galaxy, and the dearest of it inside this one room. A vast dark page makes one line of writing impossible to miss. You are on the line. Everyone you love is on the same line. And take, last of all, the sheer size. The fact that broke every intuition you started the night with. Here is its gentle side. Every light year of it was measured from here, not from some cosmic center, because the standard picture has none. From here, leave it at her desk, Slipher at his spectrograph, Hubble at his eyepiece, Geller and Hukra with their slice of sky, the supernova hunters, the 5,000 small robots of Desi aiming their fibers at the dark, all of them measuring outward from this one small world, patiently, for a century, until the whole address was known. The universe did not hand us the map. A few thousand careful people, on one planet, in one spiral arm, drew it, and tonight, lying still, doing nothing but breathing, you inherited it. You are among the first generations of your species. Out of all the thousands that ever slept beneath this sky, to actually know what the sky is. Let me be honest, one final time, because the honesty is the gift. When I say the garden is fenced, and the line of writing holds everyone you love, that is not a scientific conclusion, so much as a human way of holding the science. The measurements are real. The comfort is a choice about where to rest your attention among them, but it is not a false choice. Nothing tonight required exaggeration to become consoling. The bound stays bound. The quiet is real. The map was drawn from your doorstep. The universe spends its almost endless room on silence and dark, and then, in a few scattered threads, it gathers everything warm into close company. And you were born in the gathered part. The worse the distances get, the more clearly that shows. Nothing tonight was ever a threat. It was, in the end, a very long way of saying that you are home. And that home, for as far ahead as anyone can honestly see, is not going anywhere. The journey is complete now, and nothing more is asked of you. Whatever numbers came along tonight have already done their work, and they are free to go. The light years, the megaparsecs, the ages and the surveys, all of it can loosen and drift off, the way a day loosens its grip the moment you stop holding it. If one thing stays, let it be the shape, bright, then dark, then bright again. Small, warm rooms strung along quiet threads, with room to breathe between them. That was the whole map. That was always the whole map. Above your roof. Right now, the ancient light of Andromeda is coming down through the dark, finishing a journey of 2.5 million years, falling on sleeping fields and empty roads, asking nothing of anyone. Far out in the countryside between the galaxies, an orphan star is carrying its small, steady light through the quietest landscape there is. And it is not lonely, because loneliness needs someone to notice. And out there, no one is keeping watch. Somewhere much farther away, light is leaving a galaxy we will never be able to answer. And it is coming here anyway. And in some distant autumn, it will arrive. And someone will look up, and that will be enough. And through all the widest places in between, space itself is quietly widening, the slow exhale of the universe, while every gathered place, ours among them, keeps its own warm counsel and stays. The expansion will not pause if you fall asleep before this sentence ends. The local group will hold its shape whether or not you remember its name by morning. That was the deepest comfort hiding under everything tonight. Not that the universe is small enough to hold, but that the part worth holding was here the whole time, in the room, within reach, bound to you by forces the widest darkness cannot touch. If tonight's journey gave you a little wonder, or made the dark outside your window feel less like an absence and more like a wide, calm countryside between friendly towns, you are always welcome to stay a while and to travel these quiet distances with us again on another night, but there is no task left in that, and no hurry, if all you do now is sleep. That is a perfectly good use of a universe. Wherever you are, the room is real, and close, and yours. The distances are real too. Every unthinkable one of them, and not a single one was ever aimed at you. Let the day finish setting itself down. Let your thoughts drift apart softly, like galaxies loosening across a wide and patient dark, in no order anyone needs to fix. The space between galaxies will keep growing all night, gently, out where nothing is holding on, and here, where everything is holding on. The space between you and rest has never been smaller. Good night, from space serene. Sleep well, in the gathered part of the universe.